So, section 4.4, derivatives of exponential and log functions. On the side, you see the list of all the functions we are going to look at. The power rule for arbitrary real powers, not something that I take the time to do. It is just power rule again. So, we'll be looking at e to the x, a to the x, natural log of x, and log base a of x. So, to begin, the number e you have seen defined in previous classes. What's the value about 2 point? Press those calculators. 2 point what?
2.71.
Okay. So, and it is one of those irrational numbers that is a non-terminating, non-repeating decimal. One of those strange numbers. And it is a number, hush folks. It's a number that shows up in the world in strange places. Just pops up from time to time. So mathematicians like pi, mathematicians use it quite often to help lead to other things. So if I were to have you graph e to the h minus 1 over h, playing around, that looks like a difference quotient, looks like it might have something to do with the derivative. If I were to have you graph that and take the limit as x goes to 0, we could graphically prove that that limit goes to 1. Okay? And having that as our basis, it makes taking the derivative of e to the x far easier. So, let's take the derivative of e to the x using our definition of a derivative. So, you will have, what is the definition of derivative? Oh, hold on. Limit is the first word I want to see. The limit as h approaches 0 of, careful, what is it for e to the x then? E to the x plus h minus e to the x all over h. Okay. And then what can I factor out of the top two terms? What can I factor out? E to the x. So we have the limit as h approaches 0 of e to the x. And what am I left with? E to the h minus 1 over h. Now our variable that we're working with here is what we have underneath our limit. So what can I do with this e to the x then? Treat it like a constant and pull it to the front. And we said from the beginning, if we graphically look at this, this limit would equal 1. So the derivative of e to the x is? It is e to the x. So, it is officially your favorite derivative of the year. I know. Nothing tricky. There's nothing funny about it. It just is. So if we looked at the slope of the e to the x function at any point, quietly, and then we decided to graph those points, we would get the exact same curve. Just magical. All right. So now, the one thing I have to remind you about, sorry?
Wouldn't that happen to any number range we have?
Not quite. Not quite. There's a similar relationship, but not perfect. It is not.
Only with e?
Only with e. Yes.
What about pi and other constants?
Doesn't work. Nope, they just have a constant out in front, pi to the x. Listen up, folks. If we take the derivative of pi to the x, we will use a different formula that we call a to the x.
Because only e to the h minus 1 over h equals
Right.
1.
That's the only one where this relationship will hold. Okay? All right. Stop making me say be quiet. All right. Now, something to remind you about. Remember I said, if you have to take the derivative of a trig function of anything other than just x, you need, okay, like sine of 3x, I need to apply what? Chain rule. So, if I have e to anything other than just x, the same thing applies. You need chain rule. So, make a note of that, please. Derivative of e to anything other than just x requires chain rule. Okay? And that's because it's a composition of functions. E to the x is the parent function. E to anything else in terms of x would be a composition. So if we want to find the derivative with respect to x of y equals e to the x plus x squared, dy dx would equal what? So you take the derivative of the outside, leaving the inside alone. E to the x plus x squared times 1 plus 2x. That's it. So, a few years ago I had to take a graduate class, and it was the basics of statistics. And in statistics, you use a lot of calculus, finding the area under the curve, to find probabilities of certain things happening. And all very interesting, but a few of the people in the class had not taken calculus in a few years. It was very nice of me, because you all keep me in my calculus. But the girl next to me, we were taking a partner quiz or something, and we had to take the derivative of e to the x, and how do we do that? Parallel doesn't apply. Please. The nice one we had, they were all smarter than me and everything else in that class. But e to the x, I got it. All right. So, just a little. All right, moving on. Now, the next one we want to take the derivative of is a to the x. And to do this, we need to believe that a to the x is the same as e to the x times natural log of a. And if I take one more step and apply the log properties that we know, that is equivalent to e to the x natural log of a, is it not? Because with log properties, if I have the log of something to the x, can I bring that something down in front? And it's equivalent, right? So, and what happens when I have e to the natural log of something? Cancel, or they undo each other? So, e to the natural log of a to the x is a to the x. So, do we believe this to be true? Thank you. I believe it to be true. So now, it makes it far easier to take the derivative, now that we know the e to the x rule, of e to the x natural log of a. A few things we need to make clear. A is a constant. Not a variable. It's 2 or it's 7. Right? A is a constant. So, if I want to take the derivative of this, what do I get? Apply the chain rule. Derivative of the outside, leaving the inside alone, becomes e to the x natural log of a times the derivative of the inside which would be a is a constant, so that means the natural log of a is a constant. So it's not just x, it's okay, hold on. Listen, how do I take the derivative of 3x? What is that? 3. So what is the derivative of natural log of a times x? It is the natural log of a. All right, and to be helpful with format, e to the x log a is e to the x. So, the derivative of a to the x is the natural log of a times a to the x. So, very similar, but off by a stretch factor. There's your second derivative of the day. Okay? So we've learned e to the x, we've learned a to the x. So I don't think I have an example next, so I might toss one on here. Come back. So let's put an example here. Let's say I wanted you to take the derivative of 2 to the x squared plus 4. The derivative would be what? We start with natural log of a, which is what in this case? 2, thank you. Natural log of 2 times 2 to the x squared plus 4 times 2x, thank you. We have to apply that chain rule, times 2x. The chain because it's not just to the x, but to some other function. So it's a composition in that form. Yeah, you can read it like that. How do you get what? Are we okay? Okay.
We define the natural log without having to use a calculator.
No. So you will write natural log of 2. Okay. All right, other questions on this one?
Was it Newton that figured stuff out?
Some of it. Leibniz also figured out some of it, and then they battled over publishing rights and who gets credit. But you'll find that out. So, moving on. All right, come on, we got to get through these others. Okay, the next one that we want to take the derivative of is natural log of x. All right, and to do that, we start with the function y equals natural log of x. And it's helpful to us because we've already figured out how to take the derivative of e to something to write this in exponential form instead of log form. So if y equals the natural log of x, then that means e to the y equals x, correct? Okay, so that's our first step in this one. Then we are just doing implicit differentiation the way we have for the past few nights. Okay? So the derivative of e to the y would be what? E to the y times dy dx equals what? 1. And solve for our dy dx. And we get 1 over e to the y. And what is e to the y equal to? It is equal to x. So this is the second best one. So the derivative of natural log of x is 1 over x. Okay? All right, so a quick example for that one. And of course, I'll do it with chain rule or something else involved. So let's say we needed to take the derivative. We want to find y prime if y equals the natural log of cosine of 2x plus 3, because we don't want to start simple. We want to challenge. Try it at your desk first, please. So we are looking for y prime. And we clearly have chain rule, correct? The outside function is natural log, so we begin with what? 1 over that whole thing. Cosine of 2x plus 3 times?
Negative sign.
Very nice. Negative sine of 2x plus 3 times 2. Okay? Because that's fun, I know. You can simplify, but you don't have to. Stop the mumbling. Hush. Last one. All right. Any question on that one? So for tonight's homework, you should have the derivative of e to the x, the derivative of a to the x, the derivative of natural log of x, and the derivative of log base a to the x at the top of your page. There's the 4 new ones. Just have them at the top, make it easier to get through. So the trick to taking the derivative of log base a of x is to use this. What's that called? Thank you. Base change formula, or change of base. Again, remember, a is a constant. So we want to take the derivative with respect to x of log base a of x. So it will help us to first write it as the derivative of natural log of x over natural log of a. Okay? Avoid the quotient rule. We're going to beat that into the head. We are going to avoid the quotient rule. A is a constant. What can I do? Thank you. We can pull the 1 over ln of a out in front. Because a is a constant, so natural log of a is a constant, times the derivative of natural log of x. So we get 1 over the natural log of a times what? 1 over x. So you may see that written as derivative of log base a of x equals 1 over x natural log of a. So there is our fourth new derivative rule. Okay, everyone needs to pay attention on the next slide, because it is a very powerful technique for taking the derivative for a certain type of function. So do we have any questions on this? We're okay? I can. I'm moving on. All right, so the last thing we need to talk about, I guess I had an example. Yep, we'll do an example. All right, dy dx, find dy dx if y equals log base a of a to the sine x. Do this at your desk right now, and don't say anything while you're doing it. Try to flip to the paper, Michael. Go. Well, I just gave you a rule a second ago. For log base a. You know what to do. All right, so look up here. So if we are taking the derivative of log base a of x, then we have to apply the rule 1 over x log a. Quiet, please. But we certainly could do this in a simpler way on this problem. What is log base a of a to the sine x equal to? Just sine x. Y prime is equal to cosine x. So look for those easy little relationships to make life a little bit easier. I'll step through and show this side once I get through my next problem. All right. So the next thing I want to talk about is where you need to pay close attention. All eyes forward, no one talking. This is called logarithmic differentiation. So we have done a lot of derivative rules. Power rule is when we have x to a number, correct? So x cubed, we know how to take the derivative of that. Using power rule, it becomes 3x squared, good. But we have now talked about when we have x to a function of x. Power rule does not apply, so write yourself a big note. Power rule does not apply when the variable is, or when the exponent is x. Or some function of x. Big exclamation points. I do not want to see you bringing an x down in front and subtracting 1 from the x on the exponent. Nobody do that. Nobody. All right. So we need to find some other way to deal with this type of function. So we have y equals x to the x. Well, we're good with product rules. So we're good with things that are multiplied together. Is there a way, or is there something that I can do with this to rewrite it so that I have multiplication instead of 2b power? And here's a little helpful hint. One more time. Close. Close. We do need to bring in log. Okay? So, what we can do to this equation, if we do it to the left side and do it to the right side, the equation is still equivalent and balanced. So what we can do is we can take the log of each side of the equation. We certainly want to bring in log so that we can apply the log property that brings an exponent down in front. Okay? So if I have natural log of y equals natural log of x to the x, what can I do? It's that. The log property says the exponent can be written as a multiplier in front. And we have this. And now, implicit, yes.
So we can put ln x and y.
No, not quite yet. Because y is x to the x, not ln. But we can take the derivative of all of this using implicit. Okay, so we want to take the derivative of all of this using implicit differentiation. So what is the derivative of natural log of y? 1 over y times dy dx equals, what will I need over here? Product rule. I'll need product rule. X times natural log of x. So, first times derivative of the second would be x times what? 1 over x. Plus the second, ln of x, times the derivative of the first, which is 1. So let's clean it up a little bit. We have 1 over y, dy dx, equals what? Plus natural log of x. Okay, almost there. Dy dx equals 1 plus natural log of x times what? Y. And now, Natalie, what you were thinking about, what is y equal to from the very beginning of the problem? Y is equal to x to the x, right up here. So we get 1 plus natural log of x times x to the x. So if we can get all the way back in terms of x's, we do. I know we've had some derivatives where we've had x's and y's when we do implicit. If possible to get back to all in terms of x, we do. So that method of taking the log of each side and then implicitly differentiating is called logarithmic differentiation. You use it when there is an x in the exponent. Okay? All right. So I say when there is an x in the exponent with an x in the original, the base as well. Okay? All right. So you have a bunch of new rules. And what time am I at? Okay. About 10 minutes. Okay, so let's get our assignment sheet up and see what the homework is for today.